Based on the discussion of n behavior, match each function with its graph. So for this one, we have f of x equals x to the fourth minus x squared plus 5x minus 4. Now I can figure out which graph this is without looking at the last terms. So I'm going to ignore the last three terms. They don't really matter when we're looking at the n behavior. We know this is an even power, so it could both face up or both of them could face down. Now, since there's no negative in the front, it must be the first case where both of the tails face up. So the graph here is C. We don't need to graph it in order to know that it must be C, because this is the only one where both of the tails face up. We look at the leading coefficient again. We have negative x to the sixth. And I know since this is even, both of the tails are either facing up or facing down, but there's a negative in the front, so that's going to cause it to be the one where it faces down. Because g is of even degree with negative leading coefficient, the graph must be graph A. In h of x equals 3x cubed minus x squared plus 2x minus 4, I want to figure out which graph it is. I look at the power, it's odd, and the number in the front is positive. So I know it's going to look something like this, where the tail is on the left, and the right side has to have a tail going up. So it must be graph B. Because function h has odd degree and has a dominating term that's positive, its graph must be graph B. Let's look at k of x being equal to negative x to the 7th plus x minus 4. Now we have a negative in the front, and this is an odd power. Since this is an odd power, I have two possibilities. The tail could go to the left and then go up, or be up then go down. I know it must be the second case since there's a negative in the front. So I know the tail on the left has to go up and the tail on the right has to go down. So the graph looks like graph D. So let's look at the summary of how we're going to graph functions of the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way to a sub 1 x plus a naught, and here the leading coefficient cannot be 0. To sketch this graph, we have to follow the steps. We have to find the zeros of f of x, plot them as x-intercepts. We want to find f of 0, and that's equal to a naught, or the y-intercept. In step 3, we're going to use n behavior, determine whether the graph crosses, bounces on, or wiggles through the x-axis at the x-intercepts, and selected points as necessary to complete the graph. In example 3, we're going to graph a polynomial function, f of x equals 2x cubed plus 5x squared minus x minus 6. To begin, we'll use the rational root theorem. We have 6 is p and 2 is q. So we'll look at all the factors of 6, which are 1, 2, 3, and 6. And we'll look at all the factors of 2, which is 1 and 2. The possible rational roots are then plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 1/2, and plus or minus 3 over 2. Remember, we're taking all of the values p and we're putting it over the values of q, and that's how we get these lists of the rational roots. And that's how we get the list of possible rational zeros. We will now use synthetic division to show that 1 is a 0. Now, how did I know 1 was a 0? I used guess and check. Basically, I started plugging in values from my list of possible rational zeros. And I thought, hey, 1 is a very easy number to use. So I plugged in the 1 into the x values, And when I did the math, it gave me 0, so I know 1 is a 0. So I'll use synthetic division now with 1. So now let's go over the process of synthetic division. We have the 1 is on the outside, and on the inside it's 2, 5, -1, and -6. So we'll drop down the 2. 1 times 2 gives us 2. 5 plus 2 gives us 7. And 1 times 7 gives us 7. -1 plus 7 gives us 6. And 6 times 1 gives us 6. -6 plus 6 gives us 0. We were expecting that the remainder is 0 because when we did f of 1 on a calculator, we know it's supposed to give us 0. So this is our remainder, and it will allow us now to factor 2x cubed plus 5x squared minus x minus 6. This implies that 2x squared plus 7x plus 6 must be a factor of our function f of x. And thus, we have f of x can be written as x minus 1 times the quantity 2x squared plus 7x plus 6. We now can use the AC method. 2 times 6 is 12, and the 7 goes on the bottom. We're looking for two numbers that multiplies to get 12 but adds up to 7, and those two numbers are 3 and 4. We'll use the AC method, so we'll have to divide by 2x and reduce this to lowest terms. The first one is already reduced. The second one becomes 2 over x, and according to the bottoms up method, we can bring the 2x to the top and the x to the top. So we have f of x is equal now to x minus 1 times 2x plus 3 times x plus 2. Set each linear factor equal to 0, then solve for x to find the zeros. I can set x minus 1 equal to 0, 2x plus 3 equal to 0, and x plus 2 equal to 0, and solve those values for x. So my three zeros are 1, -3 over 2, and -2. In step 2, we're going to use the fact that if I plug in a 0, f of 0 just gives us -6. So we'll plot 0, -6. We'll also plot our zeros, -2, 0, -3 over 2, 0, and 1, 0. These are our zeros from our synthetic division process. And we know since the exponent is odd, the end behavior is going to have a tail on the left, and the tail on the right is going to go up. So the tail on the left is going to go down, the tail on the right is going to go up because of this odd power, and the coefficient is positive. Since the dominating term of f of x is 2x cubed, the graph will have end behavior similar to that of f of x equals x cubed. It will rise to the right and falls to the left, as this symbol here shows. Each zero of f of x occurs with a multiplicity of 1, meaning that the graph of f of x will cross the x-axis at each of its zeros. Because the graph of a polynomial function has no breaks, gaps, or sudden jumps, we now have sufficient information to sketch the graph of f of x. Begin the sketch at either end of the graph with the appropriate end behavior, and draw a smooth curve that crosses the x-axis at each zero, has a turning point between successive zeros, and passes through the y-intercept as shown. So we have the zeros -2, -3 over 2, and 1. We plot the zeros first, and I plot the y-intercept, which was 0, -6. I know that the left side has to be down and the right side has to be up. So we'll start by traveling from the left side upwards, and we know it has to cross -2 and then come back down at -1 because we have a multiplicity of 1 for each of those. We know it must cross 0, -6, and finally it must also shoot through the 1 here. So this is a rough sketch of the graph. And again, if you want to graph these on a computer, go to desmos.com. Example 4, let's graph f of x equals negative x minus 1 times x minus 3 times x plus 2 squared. We will start by looking at the zeros. It's already factored, which is convenient, so we can look at these values here and automatically find our zeros. Since the polynomial is given in factored form, the zeros can be determined by inspection. They are 1, 3, and -2. Plot these as x-intercepts of the graph of f of x. And here we have plotted the points. We have the point -2, 1, and 3 for our zeros. In step 2, we could also find additional points. So let's plug in an easy point to use, 0. F of 0 is equal to -0 minus 1 times 0 minus 3 times 0 plus 2 squared. 0 minus 1 simplifies to -1. 0 minus 3 is just -3. 0 plus 2 is 2. So we can simplify this to -12, and that means we can plot the point 0, -12 on the y-axis. So we have a zeros -2, 1, 3, and now we have a y-intercept 0, -12. We're almost done. All we need now is to consider the end behavior. The dominating term of f of x can be found by multiplying the factors and identifying the term of greatest degree. Here we have the leading term can be found by multiplying -x, x, and this term is equivalent to x squared. So we can multiply -x, x, and x squared, and -x to the fourth will be the leading term of f of x, indicating that the end behavior of the graph is both facing down because this is an even power with a negative leading coefficient. Because 1 and 3 are zeros between the multiplicity of 1, the graph will cross at these zeros, and the graph of f of x will touch the x-axis at -2 and then turn and change direction because it's a zero of even multiplicity. What that means is, since the multiplicity of x equals 1 is 1, and the multiplicity of x equals 3 is 1, since the exponent here is 1, it's going to shoot through for these x-intercepts. But since this is an even multiplicity, x minus 2 is going to bounce off at the point x equals -2 because of the even multiplicity. In step 3, we begin at either end of the graph with the appropriate end behavior and draw a smooth curve that crosses at 1 and 3 and touches the x-axis at -2, then turns and changes direction. The graph will also pass through the y-intercept -12. Here is our finished graph. We know that the tails have to be both facing down because we know our leading coefficient is even with the negative number in the front. I know when I approach -2, I cannot shoot through it. I must bounce off of it because of the multiplicity of 2. As I head back down, I know I must cross the y-intercept, 0, -12. And then at the 0, 1, we know I must shoot through it because the multiplicity is 1. And at some point it must make back a turn, and we must shoot through the 0, x equals 3. And of course our tail heads downward as we go to the right. So that's the process. Always start with the endpoints first, and then start with your zeros and your y-intercept. Look at the multiplicity. If it has a multiplicity of 1, it shoots through it. If it has an even multiplicity, like here at -2, it will bounce off of it. The intermediate value theorem for polynomials. If f of x is a polynomial function with only real coefficients, and if for real numbers a and b the values f of a and f of b are opposite in sign, then there exists at least one real zero between a and b. What that is saying is essentially if f of a is a point on the graph that is below the x-axis and f of b is a point above the x-axis, then at some point we have to cross the x-axis if our function is continuous, so there must be a zero between the point A and B. Use synthetic division and a graph to show that f of x equals x cubed minus 2x squared minus x plus 1 has a real zero between 2 and 3. So we'll use synthetic division with 2 and 3. Using synthetic division, I have 2 on the outside, 1, -2, -1, and 1 on the inside. We'll drop down the 1. Multiply 2 times 1, and that's 2. -2 plus 2 is 0. 2 times 0 is 0. And -1 plus 0 is -1. 2 times -1 is going to give us -2. And adding this, we get -1. So f of 2 is -1, a negative number. We can do synthetic division again now with 3. When we use synthetic division with 3, we'll drop down the 1. 3 times 1 is 3. -2 plus 3 is 1. 3 times 1 is 3. -1 plus 3 is 2. And 2 times 3 is 6. When we add this, we get f of 3 is 7. What this means is, if I were to graph the values, at 2, we have the function value is at -1, and at 3, the function value is at 7. And so, we have one value that is below the x-axis, one value that's above the x-axis, so at some point we know it must cross the x-axis and have a zero between there. So according to the intermediate value theorem, there has to be a real zero between 2 and 3. The boundedness theorem. Let f of x be a polynomial function of degree n greater than or equal to 1 with real coefficients and with positive leading coefficient. Suppose f of x is divided synthetically by the factor x minus c. If c is greater than 0, and all the numbers in the bottom row of the synthetic division are non-negative, then f of x has no zero greater than c. How is this useful? Well, if I know there's no zeros greater than c, then I can use trial and error to test the other zeros that are less than c. B. If c is less than 0 and the numbers in the bottom row of the synthetic division alternate in sign with 0 considered positive or negative as needed, then f of x has no zeros less than c. If there are no zeros less than c, then we can check all of the zeros above c if there are any left. Example 6, we want to show that the real zeros of f of x equals 2x to the fourth minus 5x cubed plus 3x plus 1 satisfies these conditions. There are no real zeros greater than 3. Since f of x has real coefficients and the leading coefficient is 2, is positive, use the boundedness theorem, divide f of x synthetically by x minus 3. So we have 3 divided into f of x synthetically. We'll bring down the 2. 3 times 2 gives us 6. -5 plus 6 is 1. 3 times 1 is 3. 0 plus 3 is 3. 3 times 3 is 9. 3 plus 9 is 12, and 3 times 12 is 36. So we have a remainder of 7. Notice all of these values are non-negative. They're all non-negative. Since 3 is greater than 0, and all the numbers in the last row of the synthetic division are non-negative, f of x has no real zeros greater than 3. B. Show there are no real zeros that are less than -1. We'll use synthetic division, and we will divide f of x by x plus 1. So we have the -1 on the outside, and I'm going to put the coefficients 2, 5, 3, and 1 on the inside. Here we need a placeholder of 0 because there's no power of 2 will have a placeholder of 0. So we'll drop down the 2, multiply, -1 times 2 is -2. Then we add, -5 minus 2 is -7. -7 times -1 is +7. Add again, we get 7. -1 times 7 is -7. 3 plus -7 is -4. And -4 times -1 gives us 4. And we add, we get 5. Notice that we have alternation in sign. We have a positive to a negative, then a negative to a positive, then a positive to a negative, and a negative to a positive. So the last row alternate in sign. Since -1 is less than 0, then there is no 0 less than -1.